All right, let's dive into a genuine mystery from the world of nanoelectronics. It's a real head-scratcher, something that seems like it should be impossible. What happens when electrons start to flow backward?
Think about it for a second. The tiny little switches that power everything. Your phone, your laptop, even giant supercomputers. What if they just broke the rules? What if they started running in reverse? Well, that's exactly the strange anomaly we're going to unpack.
Okay, so before we get too deep, let's make sure we're all on the same page. The main character in our story is the transistor. And really, you can just think of it like a tiny microscopic faucet for electricity. You turn the knob, that's called the gate, and you control how much current flows through. Sounds simple enough, right? Yeah, well, usually it is.
So to really get why this whole thing is so weird, we need to understand how things are supposed to work. Let's take a look at the normal rules of the road on the electron superhighway. For decades, physicists and engineers have relied on this one model. It's called drift diffusion, and this thing has been the absolute law of the land for predicting how electrons are going to move around. It's been super reliable, with one little catch. It only really works perfectly as long as the transistors are bigger than, say, 80 nanometers.
And this model is actually pretty straightforward. It's all based on two main forces. First, you've got drift. That's where an electric field just pulls the electrons along, kind of like the current in a river. And then you have diffusion. This is just the natural tendency for electrons to spread out. They move from a really crowded area to a less crowded one. And for a long, long time, these two forces, they explain pretty much everything we saw.
Yeah, diffusion is super easy to picture. Imagine a packed concert venue when the doors open. Everyone just naturally spills out into the empty space outside. Electrons are supposed to do the exact same thing, flow from where there's a lot of them to where there are fewer. It was predictable, it was reliable, or so we thought.
All right, now let's get to the scene of the crime, because this is where the physics rulebook got thrown right out the window.
The transistor where this all went down was unbelievably small. The channel was just 34 nanometers long. I mean, to put that in perspective for you, that is more than 2,000 times thinner than a single human hair. We are talking seriously, seriously small here. We're deep in the nanoscale. And here it is, the shocking discovery. And this is a quote pulled right from the research paper. In this tiny, tiny transistor, the electrons just reversed course. Instead of flowing from the source to the drain, which is the way they're always supposed to go, they started flowing backward, from the drain back to the source. Absolutely wild.
So this is the really critical part. It happened under very specific conditions. As the researchers cranked up the gate voltage, turning our electrical faucet on harder, the flow didn't just get stronger. It actually flipped around and went the other way. The current went negative. I mean, that's just not supposed to happen. This completely flew in the face of everything engineers and physicists expected. So naturally, an investigation started, and the number one suspect?
The rulebook itself. And the conflict here couldn't be more stark. On one hand, you have the classic drift diffusion model, the one that everyone trusted. It predicted a nice, steady, positive current. But on the other hand, you have what they actually measured in the lab, a negative current. The model wasn't just a little bit off, it was completely wrong.
The physics they were using just had no explanation for this. It was literally like watching a river decide to flow uphill. It was pretty clear that some other force, something the old models couldn't see, had to be at play.
And this is where we get the big breakthrough. The solution to the mystery wasn't found in classical, everyday physics. Nope. It was hiding in the weird, wonderful, and often counterintuitive world of quantum mechanics. The hero of our story, the theory that finally cracked the case, is called the density gradient model, or DG theory for short.
So, what exactly is this DG theory? Well, you can think of it as drift diffusion version 2.0. It takes the old model as a base, but then it adds this incredibly important new layer on top, quantum effects. See, these are effects that you can totally ignore in bigger transistors. They just don't matter. But once you get down to the nanoscale, they don't just matter, they start to run the show.
Okay, so now we have our new detectives tool. Let's see exactly how this quantum plot twist finally solves the mystery.
It turns out the hidden force, the real culprit here, was something called a generalized quantum potential. Now, that sounds complicated, but you can just think of it as a weird kind of quantum pressure. It's a force that only shows up when you squeeze electrons into a ridiculously tight space, like, a 34 nanometer channel.
So here's how it works, step by step. First, at a low gate voltage, this quantum force is pretty weak. It's there, but it doesn't do much, so the current flows normally. But then, as you crank up that gate voltage, something weird happens. The quantum potential actually flips, and it creates what you can think of as an invisible hill. It's like if turning your faucet on harder suddenly created a wall of pressure in the pipe that pushed the water right back out at you. And this new quantum force is so strong, it actually overpowers the normal flow and pushes the electrons backward, completely reversing the current. And here's the best part. When the researchers plugged this new density gradient model into their simulations, the one that accounts for this quantum hill, the results were just perfect. The model predicted the exact negative current they were measuring in the real world. Case closed. The mystery was solved.
Okay, so you might be thinking, why does one weird little transistor matter so much? Well, it matters because it's proof positive that the super strange rules of quantum mechanics aren't just in textbooks. They are actively affecting the devices we use every single day. If we want to keep Moore's law going, if we want to make our chips even smaller, faster, and more powerful, then we absolutely have to understand these quantum effects. Discoveries like this are a huge deal because they help engineers figure out what's coming next and maybe even use these bizarre effects to their advantage.
And that really leaves us with a pretty mind-bending thought, doesn't it? This was just one unexpected quantum ghost hiding in the machine. It really makes you wonder, what other quantum secrets are hiding inside the devices we use every day, just waiting for us to find them?